In the previous chapter, we defined mechanical energy as kinetic energy that an object has plus its potential energy. Expression for kinetic energy is 1/2 of mv squared, and previous chapter we dealt with gravitational potential energy, which is given by mg y minus y naught, where y naught is the zero reference level that we choose for our gravitational potential energy, i.e. Ug is 0 at y equals y naught. And y is the vertical position of the object. Now, if frictional forces are non-existent, in the absence of friction, then the change in the mechanical energy of a system is 0, i.e. change in the kinetic energy is equal to negative of the change in the potential energy of the system. And we used this argument to, for example, figure out the speed of an object at the bottom of a ramp, knowing the change in the potential energy of the gravitational potential energy of the object going from this initial position to this final position, so we can figure out what the final speed of the object is, for example, because the change in the gravitational potential energy will equal the change in the kinetic energy of the object. So knowing the initial velocity speed, we can figure out the final speed. Now, in this lecture, we're going to introduce spring potential energy. Us, which is the potential energy that an object has by virtue of its being in contact with a spring, which is either stretched or compressed. So if we let's consider a spring which is right up against a wall. Let's say that spring has a length L. It's a spring in the horizontal, and we have an object with mass m in contact with the spring. Now, so let's call the situation A. Now, if we push m against the spring, then we compress the spring. Or we could stretch it, and now let's consider these three different scenarios once again. When the spring is compressed, then we know that by experience that there is a force. Let's call that F spring. There is a force in the positive x direction on mass m, and if we when the spring is stretched, then the spring force is in the negative x direction. In the spring force Fsp is always such that it points towards the equilibrium point. Now, this equilibrium point, which I will call x naught, is the natural length of the position of the spring, the position where the tip of the spring is when it's neither stretched nor compressed. So x naught is the the equilibrium position for the spring. In scenario B, when the spring is compressed, then there exists a spring force on our object, which points in the positive x direction, once again is towards the equilibrium position. And in scenario C, when the spring is stretched, then FSP switches sign and points in the negative x direction. Now, so this spring force is not only proportional to the amount of compression or stretching, that's x minus x naught, but how much it's compressed or stretched, but it's proportional to the negative of x minus x naught. The negative sign here implies that the spring force, if the in scenario B, notice that x minus x naught is negative, which means that and our spring force is positive, is towards in the positive x direction. In scenario C, x minus x naught, our x is here, x minus x naught is positive, and the spring force is negative, is pointing away from the positive of the x-axis. So spring force is proportional to negative of x minus x naught. The more you compress or stretch the string, the greater the magnitude of the spring force. And the spring force is given by minus k x minus x naught, where k is a constant. It's a spring constant. Its units are newtons per meter, and the spring constant is a measure of the stiffness of a particular string. So the greater the k value, the stiffer the spring is, and the smaller the k value, the less stiff it is. So if you were to plot spring force versus extension x, then for different springs, it's supposed to be a straight line, for different springs we would have different curves like this. So the blue spring has a greater slope, which means that it's a stiffer spring than the black spring, and the black spring is more stiff than the red spring, and so forth. So the greater the k value, the stiffer a particular spring is. Now this relationship, if spring is equal to minus k x minus x naught, is known as Hooke's law. Although it's referred to as a law, strictly speaking it is not a law, because it's only valid for x minus x naught in the range of 10 to 15% of the length of the spring. So if you compress or stretch a spring by more than 10 to 15% of its length, then this relationship is not valid. It deviates from this relationship. So strictly speaking it's not a physical law, but historically it's always been referred to as Hooke's law. Now let us consider the potential energy associated with the spring force. So once again, this is our x direction. Up against the wall we have the spring whose with a spring constant k, let's say, and we have a mass m which is pushes right against the spring. And the spring, first thing that you need to do in a problem involving a spring is define or know where your equilibrium position is, x naught. So that's the natural length of the spring right there. Okay, so the spring is compressed by the amount x minus x naught. So this here is our change in the length of the spring, which is the amount of compression in this case. And when we let go of the mass m, then the spring relaxes back to its natural length, and our mass takes off with some velocity v final. So initially v initial is 0, and then v final is, let's say, is what we are trying to figure out, which is equal to 1/2 of mass. Oops, I'm sorry. It's v final, not k final. Okay, so in our initial position we have kinetic energy initial, which is equal to 0 because our initial velocity is 0, and some spring potential energy initial, which is given by 1/2 of k x minus x naught squared. This is the expression for spring potential energy. So spring potential energy US is given by 1/2 of k square of compression, or the amount that the spring is stretched by, delta x. The units of course are again in joules, and notice that spring potential energy is a positive number due to the fact that it's proportional to the square of delta x. So whether delta x is positive or negative, spring potential energy always comes out as positive. Now for the final position, our k final is given by 1/2 of mass, velocity final squared, and US final is equal to 1/2 of k. Well, our x naught, our x is equal to x naught, so that's 0 squared, i.e. spring potential energy is 0. Assuming that there's no friction force involved along the horizontal direction, then k initial plus US initial must equal k final plus US final. After all, spring potential energy is a form of potential energy. So here we have friction is non-existent. So we have 0 plus 1/2 of k delta x squared is equal to 1/2 of m vf squared plus 0. In other words, Vf is equal to k over m square root of k over m delta x, but there's a plus or minus, so the direction is determined, of course, by whether the spring was stretched or compressed, but since in this case the spring is compressed, then of course it's the positive route because the velocity is going to be toward the positive x direction. Consider the case of an object which is pressed right up against the spring on a slope. So object has mass m, the spring has a spring constant k. Let's say this is our x naught. So that's my x direction. And this gives the amount of compression, delta x. Okay. And the slope is angle theta. Slope is angle theta. And when we let go, how far up the slope does the object reach? So you're interested in figuring out this final position, x final, let's say. Okay, so that's x initial. Now here we have the types of potential energies that are involved are of course spring potential energy. So we have a spring potential energy initial, spring potential energy final. We also have gravitational potential energy initial and gravitational potential energy final, and of course kinetic energy initial and kinetic energy final. Let me write it here. Okay. Now, since we have spring potential energy, we need to define or know where our x naught is, and we've already done so. We also have gravitational potential energy, so we need to define either the initial or the final position. Well, we need to define our zero gravitational potential level, and in this case, let's define the initial position that the object's at as our UG0. Okay, so this is 0, and kinetic energy initial is also 0 since the object is at rest to start with, and at the top of the ramp it comes to stop also, therefore kinetic energy final is also 0. Now at the top of the ramp, spring potential energy is 0 since the object is no longer in contact with the spring. The object needs to be in physical contact with the spring to have any spring potential energy. And the spring potential energy at the bottom of the ramp is of course 1/2 of k delta x squared. And the gravitational potential energy at the top of the ramp is simply mg times h. Okay, and h is x final minus x naught, or minus x initial, I'm sorry, minus x initial, which is how far up the ramp the object ends up at, times sine theta. Okay. Since we're trying to find x final minus x initial, so this is an appropriate expression to use to substitute for our h. So this is the quantity we are after. And if we assume that frictional forces do not exist, then kinetic energy initial plus UGI plus USI, now this whole thing is the total potential energy initial, must equal kinetic energy final plus UG final plus US final. So this is our final potential energy. Putting in our numbers, we have 0 plus 0 plus 1/2 of k delta x squared is equal to 0 plus mgh plus 0. So you see that the transformation that takes place is the spring potential energy that the object has to gravitational potential energy at the top of the ramp. So the initial spring potential energy of the object transforms into a final potential energy for gravitational potential energy of the object. So writing the expressions for writing the expression for H, we end up with 1/2 of K x initial minus x naught squared is equal to, the color of the pen switched, the program is acting up for some reason, x final minus x initial times sine theta. So you can rearrange this expression now to find the unknown that you were after. If you excuse me, I'm going to pause this lecture and go try figure out what is going wrong with this recording software.